sums of normal random variables. This is going to be a real important topic for us here. So here's a theorem for you, and we've actually already proven a more general case in this. Let x1, x2, up to and xn be independent normal random variables. They each have their own mean, they each have their own standard deviation. Okay, so these are all normal random variables. They just maybe have different sort of centers, different standard deviations. Okay, here's one of them centered here. Here's another one centered there, and this one has a larger standard deviation than this one. Okay. Then if I'm interested for some reason in the behavior of the sum of those things, well, I know what that is. The behavior is normal with mean sum of the means, and this is the variance. Okay, by the way, this is the variance. Be careful here. Sometimes when people use this kind of notation, they put the standard deviation over here. A lot of the probability books will put the variance over here. So this is the mean, this is the variance. Okay, so again, you read this as the sum of the xi's is distributed or behaves like a normal random variable with this mean and this variance. Okay. Yeah, and so what we proved, if you look back in one of the previous videos on moment generating function methods, I think it was the one on moment generating function methods 2, we actually proved a more general result. Said that if we take a linear combination, right, if I multiply each one of these guys by a sub I, then the result is basically the same. This sum behaves normal with mean this and variance that, right? I think that's what we did, but now for now we're just going to focus on this case in blue here. We'll just set all the a sub i's equal to 1 and just think about the behavior of the sum of those guys. So here's an example. The amount of milk dispensed into the ith 1 gallon jug is a normal random variable with mean 1 gallon and standard deviation 2/100ths of a gallon. The amounts are independent, and for a sample of, say, 10 1-gallon jugs, what's the chance that the sample mean exceeds 1.001 gallon? Okay, we could maybe make this a little more general. Let's just take a sample of n jugs. What's the chance that the sample mean x bar sub n exceeds this amount? Okay, in fact, I could even just I could change this, make it more general. Let's say x, okay, little x. And by the way, just to remind you, the sample mean, the random sample mean, if we use this kind of notation, this thing is defined to be 1 over n times the sum of these guys. Okay? All right, good. So let's write down what we're trying to find. We want to find the chance, or the probability, that the random sample mean exceeds some amount. Okay? By the way, notice that this problem is asking a question about the behavior of the random sample mean, but over here we have a result about the sum of normals being normal. Okay, well, it turns out there are at least a couple of ways to look at this. You could look at this result in terms of the sum behaving normally this way, or if this is true, then it turns out that this is the same thing, is saying, so, if I want to think about the sample mean, that's what the sample mean looks like, right? But this is just like, well, let's bring this 1 over n inside the summation there, right? And then this is this 1 to n, 1 over n times some of the xi's. So now, I can see this, see how great this is. Pretend like that's That's the AI, the A sub I for each one of those. So then I know that this thing is going to behave like a normal with mean, that's the average of the averages, and variance, that's 1 over n squared times the sum of the sigma I squared. Okay? So that's how the sample mean will behave. And if all these means are the same, then this is just mu, right? This is just mu. And if all of these, so maybe I should write that, right? If mu sub I are all the same, and the sigma I are all same, same, okay, then it's the behavior of that sum is normal with mean. Let's see, this is like adding up n mu's, right? So n times mu, n over n, that just gives me mu. And then here I'll have, this is like adding up n sigma sub I squared. So I'm, 1 over n times sigma squared, right? And that looks really familiar, doesn't it? Good. All right. So what's the chance that this sample mean exceeds x? Well, this is going to be the probability then that that random sample mean exceeds little x, right? But I know that this thing behaves like a normal, doesn't it? And since all these mu sub i's are the same, in fact, I know that we have this result here. It says that the sum of these is going to be, this thing behaves like a normal with mean mu and standard and variance sigma squared over n. Okay, so this is just the probability that, well, you know what? Maybe we could just standardize this stuff. If I take 1 over n times the sum dxi, I goes from 1 to n, subtract off the mean, that's the mean for all this stuff, it's just mu, divide by its standard deviation now. Okay, so that's sigma over root n. It's the chance that all that stuff is greater than x minus mu over sigma over root n. Okay? Now, I know how this stuff behaves. Here I've just taken a normal random variable and standardized it, right? I've shifted it by its center and divided by its standard deviation. So all of this then is the same thing as the chance that a standard normal random variable exceeds little x minus mu over sigma over root n. Okay? And now I can use this to solve my problem. Like, let's say for the special case of where n equals 10 and x equals 1.001. Okay, so for n equals 10 and x equals 1.001 gallons, and our mu is 1 gallon, and sigma was 0.02 gallons, then the probability that a sample of size 10 exceeds 1.001 gallons is just the same as the chance that a standard normal exceeds, let's see, 1.001 0.1 minus 1 gallon divided by 0.02 over root 10. I've dropped the units since they're going to cancel anyway. And so that is going to be what? 1.001 minus 1. Oh, yeah, that's just that, right? Divided by 0.02 and then times root 10. Oops. Okay, about 0.15811. About a 15% chance, 16% chance, something like that. Okay. What if I took a larger sample size? What's the probability that if I take a sample of size 20, that sample mean will exceed 1.001 gallons? Well, let's think about this two different ways. First, let's just sort of envision what's going on here. The sample mean is going to tend to cluster right around the actual mean a little bit better. So it should be less likely to be, this far away. What's the overall mean? It's 1 gallon, right? So it should be even less likely to fall at least that farther away. And in fact, you can also see this if you look at the formula here, right? What happens to this quantity here as n gets bigger? Well, you're dividing by something that's bigger in the denominator, which is like multiplying the whole thing by something that's bigger. And as you move farther and farther off to the right, the chance that your standard normal exceeds that mark it's going to be less. So this probability definitely ought to diminish. Oops, I made a big mistake. This is good because this is a mistake that a lot of people make. By people, I mean students. This is the probability that a standard normal exceeds 0.15811. Golly, don't tell anybody I did that. Yeah. All right, see that? I just computed that, put it there. Got to be really careful about that stuff. Okay, normal CDF, right? I'll just start from that answer there and go off to the right some amount, and it's a standard normal, so it's 0.43718 approximately. 0.43718. Good. Very good. All right, let's do this one here. So this will be about that. This is the chance that a standard normal exceeds 1.001 minus 1 over 0.02 divided by the square root of 20. All right. 0.001. Oops. 0.001 is the top times root 20. Okay, 0.2236. See, it's smaller, right? It's smaller. Did it again. Be careful. You guys have got to be careful with that. Okay? It's the chance that a standard normal exceeds 0.2236. Okay? So, oh 06 7 977 99999. It's about 0.411. Okay, it is smaller, not a lot smaller, but a little smaller.